Take a look at this question on your screen. We're given a vector, or I guess you can also think of it as a matrix, and this vector has two parameters, r1 and r2. The first entry over here is tan inverse of r1 over r2, and then the second entry is cotangent inverse of r1 over r2. And then based on that, we're given this double summation, right? So we're going to be summing r1 from 1 to n, and then r2 from 1 to n, and we want to find the sum of all the vectors that arise from that, right? So let's see how we can do this, and let's actually just start by taking a few small examples, right? So when we start off with r1 equals 1, we go inside that, right? It's a nested summation, and so what we're going to see is we have r1 equals 1, and then we've got the summation of r2 equals 1 until n. And again, what are we going to have here? Instead of writing out d and then sub r1 r2, I'll just write out the actual thing, right? And that's just going to be tan inverse r1, but r1 over here is 1, right? So that's going to be 1 over r2, and this is going to be cotangent inverse of the same thing. And so when we actually put in these values, what are we going to get? Well, we're going to get something like tan inverse of 1 over 1, and then we're going to add to that tan inverse of 1 over 2. Oh, so, and this should be cotangent inverse. They actually happen to be the same thing, right? Cotangent inverse and tan inverse of 1. That won't always be the case though, of course. And I don't want to write out the whole thing, but hopefully you're going to see the idea. And it doesn't seem like there's anything useful we can do with these at all, right? It actually just goes on and on and on. It's going to be infinitely many over here. Well, not infinitely many. There are going to be n of these over here, and then there are going to be n outside. So in total, how many things are we going to be adding up? Well, we're going to be adding up n squared different vectors. And so let's think if we can find something simple over there, some sort of cancellation or some sort of relationship that helps us. And one thing to notice is that this and this are going to be symmetric, right? We're going from 1 to n. So if we write down r1, r2 like this, we'll have at one point 1 comma n. At another point, we'll have n comma 1. And actually, to make it, I don't know why I did 1 over there. To make it more general, I'm just going to take over some clear space over here. For r1 and r2, we will have nk at one point, and then we'll also have k and n. Now, what's the significance of this? Well, I mean, it seems pretty obvious. Of course, we'll have 1 over 2, and then we'll also have 2 over 1. But what this actually means, remember, what are we doing? We're adding them together. So if we have tan inverse of n over k plus tan inverse of k over n, well, think about this. N over k and k over n, when you add them up, when you add up the inverse tans of them, the arctans of both of them, you're going to end up getting pi over 2. Right? And that's a very powerful property. So let's keep that in mind. We're going to get pi over 2. And, well, wait a second. We know that in total there are n squared different, and then the same exact thing applies for cotangent, right? Exact same property over here. So this is equal to pi over 2, and then this is also equal to pi over 2, right? So this is the key property. So now let's see how we can actually use this. So in the numerator, we're going to be adding up n squared different things. If you take 2 of them, now it's not going to be the first 2, it's going to be one of them and then exactly one other one of them, you're going to get this relationship. You're going to get n over k and k over n. Right now, maybe you'll have 1 comma 1, but then you'll also have 1 comma 1 come again. Right, so there'll be exactly for every combination of r1 and r2, there'll be one corresponding combination of r2 and r1 that gives you this relationship. And so in total, they're going to be n squared over 2 pairs of this. Right, they're going to be n squared over 2 pairs, and then each pair is going to have a sum of pi over 2. And then the same exact thing will hold for the cotangents, right? So we're going to have n squared over 2 times pi over 2. And then over here, we're going to again have n squared over 2 times pi over 2. And these are just the entries of the vector, right? Or the matrix, or whatever you want to think of it as. You can just factor it all out. So you get pi n squared over 4, and then just like that, we're done. So yeah, it's a pretty simple answer. It's not, a very beautiful answer. It's not like 0, 0 or anything like that, but it's still pretty, a lot more simple than what we saw over here initially in the beginning, right? And so the key idea over here was just understanding, right? Maybe you can't think of the solution right away, so you write down a few things, look for a pattern, and then once you find the pattern, you're good to go. So just wanted to share this. It was pretty interesting. Now, I didn't come up with this question on my own. I was actually watching another YouTube video with some matrices, and then it was actually bigger than this, and then you had to, take the limit as n goes to infinity. So it was a pretty complex question. This is just a small part of it. I don't remember what the video is called, but I'm going to link it in the description just so that you can watch that over as well if you'd like to see the whole thing. There's a little bit of calculus involved and then some limits. So yeah, I guess more calculus, but it's definitely worth giving that a shot. I'll try to give you the exact timestamp so you can see that. But yeah, thanks so much for watching this video. Hopefully you learned something new. If you did, make sure to subscribe. I've actually been losing subscribers recently, which is quite alarming. So please do consider subscribing. And thank you so much for watching. Bye bye.